Hello student, in this video again I am going to start with the same topic that has been discussed in the last video. It is about hypothesis testing. So we have discussed in last video that hypothesis is a claim or a statement about a property of a population. A hypothesis test or test of significance is a standard procedure for testing a claim about a property of a population. So it is basically a test to test about your claiming, about your statement. And this is a standard mathematical procedure to test your statement. And that statement might be any property on the population where you are trying to establish some property or some statement or some observation. If under a given assumption the probability of a particular observed event is exceptionally small, we conclude that the assumption is probably not correct. Try to understand this. That is very important in case of significance. It means if under a given assumption, suppose there are some assumptions, the probability of a particular observed event, probability of an event which has been observed is exceptionally small, means happening of the observed event is exceptionally small, we can say that, or we can conclude that the assumption is probably not correct. Means the assumption we are taking to find out the probability of the observed event is being very low or not correct. That is why the probability of happening that event is very small, because your assumption might be not correct. This is an example. Try to read this one. Procare Industries Limited once provided a product called Gender Choice, which according to advertising claims allowed couples to increase your chances of having a boy up to 85% and a girl up to 80%. Gender Choice was available in blue packages for couple wanting a baby boy. You guessed it. And you guessed it, pink packages for couples wanting a baby girl. Suppose we conduct an experiment with 100 couples who want to have baby girls and they all follow the gender choice, easy to use in home system described in the pink package. For the purpose of testing the claim of an increased likelihood for girls, we will assume that gender choice has no effect. Using common sense and no formal statistical methods, what should we conclude about the assumption of no effect from gender choice if 100 couples using gender choice have 100 babies consisting of 50 girls or 97 girls? So that is the example. Here we need to find out what is the probability of happening in that same pattern, 85% or 80%. So we need to use some common sense and no formal statistical methods. Then what should we conclude, or how should we conclude about the assumption of no effect? Means gender choice has no effect on having 52 girls or 97 girls from the 100 babies of the 100 couples. So that is one type of scenario where we can understand the usefulness of hypothesis testing. So we normally expect around 50 girls in 100 births. That is the from the intuition of probability. Because there might be boy or girl 50-50 sons, so normally expect around 50 girls in 100 births. The result of 52 girls is close to 50, so we should not conclude that the gender choice product is effective. So we can directly say that having 52 girls might not provide enough evidence to conclude that gender choice product is effective. If the 100 couples use no special method of gender selection, the result of 52 girls could easily occur by chance. Obviously, the assumption of no effect from gender choice appears to be correct in the case of 52 girls. There isn't sufficient evidence to say that gender choice is effective. So obviously we can state that, or we can claim that gender choice has no effect on the birth of baby boy or baby girl, because that might happen. 52 girls is almost close to 50, and that boy or girl birth might be 50% chance. So there obviously we cannot directly conclude that gender choice has a directly affecting the result of the event. So obviously we cannot our choice or our assumption might not be correct. The result of 97 girls in 100 birth is extremely unlikely to occur by chance. We could explain the occurrence of 97 girls in one of two ways. Either an extremely rare event, means 97 girls of 100 births might be extremely rare event and has occurred by chance, or gender choice is effective. So in this scenario, we might be able to say that gender choice might be effective in this scenario, but it may be also another issue is that event of having 97 girls in 100 births be a rare, extremely rare event and occurred by chance, occurred by probability. The extremely low probability of getting 97 girls is strong evidence against the assumption that gender choice has no effect. So here also, having this statement, the extremely low probability of getting 97 girl is strong evidence against the assumption that gender choice has no effect, because obviously we can assume that 100 couples might not have chosen that 97 couples might not have chosen that having girls, which is an extremely rare event. So we can directly claim that, or we can directly say that, or that evidence that creates evidence that assumption of gender choice has no effect, because obviously the couples but that percentage might be 60-40 or 40-60, but not obviously that choice should not be or may not be or might not be 97 girls. So it does appear to be effective. So that is the scenarios. One is contradicting others, or one is giving some evidence to the other claim, like that. So to understand this type of scenario, to understand this type of probability of this statement, a rare event rule for inferential statistics, that is what this example is showing, that 52 girls having 52 girls might be possible, and that directly says that there is no sufficient evidence to say that gender choice is effective. But the second one, 97 girls, shows that strong evidence against the assumptions that gender choice has no effect. So it does appear to be effective. It might be effective also. This section presents, so we have also gone through these few topics like null hypothesis and alternate hypothesis. Again, I'll try to go through it again today, and also we'll go through various more important topics and more parts to be understand, or concept to be understand in case of hypothesis testing, like test statistics, critical region, significance levels, critical value, p-value, type 1 and type 2 error. Given a claim that identify the null hypothesis and the alternate hypothesis and express them both in symbolic form. Given a claim and sample data, calculate the value of test statistics. It might be this happens in every research. Okay, given a significance levels, identify the critical values. Given a value of test statistics, identify the p-values. State the conclusion of a hypothesis test in simple non-technical terms. So to understand these things, we will go through an example. Let's again refer to the gender choice product that was once distributed by Procare Industries. Procare Industries claimed that couples using pink packages of gender choice would have girls at a rate that is greater than 50% or 0.5. Let's again consider an experiment where 100 couples use gender choice in an attempt to have a baby girl. Let's assume that the 100 babies include exactly 52 girls, and let's formalize some of the analysis. Under normal circumstances, the proportion of the girl is 0.5. So a claim that gender choice is effective can be expressed as p greater than 0.5. So only if p greater than 0.5, then only we can say that our claiming can be right, mean that gender choice has some effect. Using a normal distribution as an approximation to the binomial distribution, we find binomial because there is only two possibilities, baby boy or baby girl, that is why binomial. We find p 52 or more girls in 100 birds equal to 0.3821. Suppose that is the distribution value. Normal distribution as an approximation to the binomial distribution, we find p value. So here this is the p equal to 0.52. 52 girls among 100 is not unusual. Usually high properties of girls are those that are 0.59 or higher. Combined area of rectangles in this region is less than 0.5. So here you can see this is the critical region. Proportion of girls in 100 birds, that is the distribution, 0.4, 0.5, 0.6. We do not reject random chance as a reasonable explanation. We conclude that proportion of girls born to couples using gender choice is not significantly greater than the number that we would expect by random chance. Because if we are going for random chance, that might appear anywhere in that, or that distribution might be anywhere in this binomial distribution curve, because it's a relative frequency. So because here it is relative frequency is more than 50%, that is 52. So that might, because most of these scenario leads here, that is why we cannot say that that is a evidence for gender choice. If that is that values lies right, that values of percentage or rate of the baby girl is here, supposed to be here, then we might say that gender choice has some effect. For couples using gender choice, the proportion of girls should be greater than 0.5. That is, here you can see greater than 0.5. Then we can say that that gender choice may be some effect. Working assumption is that the proportion of girl is 0.5 with no effect from gender choice. So if the value is 0.5, then we can directly say that our assumption is that gender choice has no effect. The sample resulted in 52 girls among 100 birds, so the sample proportion is p equal to 52 by 100 is 0.52. Assuming that 0.5, we use a normal distribution as an approximation to the binomial distribution to find that p at least 52 girls in 100 birds equal to 0.3821. There are two possible, this is from the binomial distribution, this value comes from the binomial distribution value. There are two possible explanations for the result of 52 girls in 100 birds. Either a random chance event with probability 0.3821 has occurred, or the proportion of girls born to couple using gender choice is greater than 0.5. So either a random chance event has occurred, or the proportion of girls born to the couples using gender choice is greater than 0.5. So there is not sufficient evidence to support gender choice's claim. So we need to go for more formal hypothesis testing. Null hypothesis is a statement that value of the population parameter mean, such as proportion, mean, standard deviation is equal to some claim value. We test the null hypothesis directly. Either reject H0 or fail to reject H0. Alternative hypothesis is the statement that the parameter has a value that somehow differs from the null hypothesis, opposite of the null hypothesis. The symbolic form of the alternative hypothesis must use one of these symbols. If you are conducting a study and want to use a hypothesis test to support your claim, the claim must be worded so that it becomes the alternative hypothesis. So your wording on the claim should be such that it becomes the alternative hypothesis. So it's like this one. Note about identifying H0 and H1. Here H1 is alternative hypothesis, H0 is null hypothesis, or we can say HA also in case of alternative hypothesis. Identify specific claim or hypothesis to be tested and express it in symbolic term. Give the symbolic form that must be true when the original claim is false. So give the symbolic form that must be true when the original claim is false. Of the two symbolic expressions obtained so far, let the alternative hypothesis H1 be the one not containing equality, so that H1 uses a symbol less than or greater than or not equal. Let the null hypothesis H0 be the symbolic expression that the parameter equals the fixed value being considered. So that is the process to state your null hypothesis or alternative hypothesis in a mathematical form. Example, this is example. Identify the null alternative hypothesis. Refer to figure 8 to use the given claims to express the corresponding null and alternative hypothesis in symbolic form. The example we have discussed previously. The proportion of drivers who admit to running red lights is greater than 0.5. Suppose the mean height of a professional basketball player is at most 7 feet. The two claims. The standard deviation of IQ scores of actors is equal to 15. Now there are three statements. So in case of first one, the proportion of drivers who admit to running red lights is greater than 0.5. In step 1 of figure 8.2, we express the given claim as P greater than 0.5, means the value of the occurring or the chances is greater than 0.5. In step 2, we see that if P greater than 0.5 is false, then obviously P less than or equal to 0.5 must be true. That is vice versa. If this is true, this is false, this is true, this is false. In step 3, we see that expression P greater than 0.5 does not contain equality, so we can say that this is alternative hypothesis. And where this is the equal sign, because less than and equal, that is why we can say this is null hypothesis. So H0 be the P equal to 0.5, H1 be the P greater than 0.5. That is the way we need to give the null and alternative hypothesis to any claim. So second one is the mean height of a professional basketball player is at most 7 feet. In step 1 of the figures 8.2, we as per this we can say that express mean of at most 7 feet. It symbols as mu less than or equal to 7. Mean at most 7 feet. Less than or equal to 7. Mean is less than or equal to 7. In step 2, we see that if mean less than or equal to 7 is false, then mu greater than or equal to 7 must be true, or vice versa. If this is false, this will be true. In step 3, we see that the expression mu greater than 7 does not contain equality, so we let the alternative hypothesis be H1, which is mu greater than 0.5, and we let H0 be mu equal to 7. That is the null hypothesis. The third one is that standard deviation IQ scores of actors is equal to 0.5. So is equal to a 0.5. So directly we say that sigma equal to 15. IQ score sigma equal to 15. So this is equal sign. So if it is equal, then directly we can say that this is null hypothesis. And if we directly put not equal, if this is not true, then obviously not equal will be if this is not true or this is false, then obviously not equal will be true. So that will be our alternative hypothesis. Not equal, sigma not equal to 15 is alternative hypothesis, and sigma equal to 15 equal to null hypothesis, because both are opposite. If this is true, this is false. If this is true, this is false. Now we need to go for test statistics. Test statistics is a value used in making a decision about the null hypothesis, and is found by converting the sample statistics to a score with the assumption that null hypothesis is true. So our main aim here is that we need to convert, we need to find a value which can be used in making a decision making process about the null hypothesis, and is found by, that can be created. That can be created means the decision about the null hypothesis that can be done by converting the sample statistics, whatever statistics we can gather from the sample, to a score. It might be mean, it might be something else, it might be something else, but we need to convert the sample statistics to a score with the assumption that the null hypothesis is true. Our main aim is to create null hypothesis to be true. Test statistics. So test statistics for proportion, this one might be one. Test statistics for mean, this one might be one. Test statistics for standard deviation. So for, suppose you are working as a proportion, your experiment is working in a proportion environment, or you are calculating in a proportions, then you can go for this one. Or you are using mean for your null hypothesis, then you can go for this one. Or you are using standard deviations in your study, then you can go for this equation. So for different type of environment, that this formula might be different. A survey of N equal to 880 randomly selected adult drivers showed that 56%, or you can say P equal to 56, probability equal to 0.56 of those respondents admitted to running red lights. Now we need to find the values of these test statistics for the claim that the majority of all adult drivers admit to running red lights. Means our claim is that majority of all adult drivers admitting to running red lights. So if our alternative hypothesis will be P greater than 0.56 or P less than 0.56. In section 83 we will see that where there are assumptions that must be verified. For this example, assume that the required assumptions are satisfied and focus on finding the indicated test statistics. So our aim is to find the test statistics, and our aim is to find the assumptions. Then only you can go for hypothesis testing. The preceding example showed that the given claim result in following null and alternate hypothesis, as like the previous examples. H0 null equal to obviously 0.5, because equal symbols associated with the null only, but not with the alternative one. H1 should be P greater than 0.5, because we work under the assumption that null hypothesis is true. That is why this will be true, only this is false, and this will be false, only this is true. So assumptions that the null hypothesis is true. So with P equal to 0.5 we get the following test statistics. Here 0.56 is our actual p value, or the finding p value, and our null hypothesis p value is 0.5. So you can use this, and the value is z value is 3.56. So interpretation is that we know from the previous chapters that z score of 3.56 is extremely large. Means when the z score is 3.56, which is exceptionally large, it appears that in addition to being more than half, the sample result of 56% is significantly more than 50%. So here you can see usually high sample proportion, this part, this area. So 1.645, if z equal to 1.645, this is the area. And when this is z equal to 0 or 0.5, so in that way, in this direction Z value changes. So 0 to 1.645, this is the area, but more than this value, means more than 1.645, whatever the value is, we can say that the value of Z is significantly higher. That's what it is saying in the previous slide. See, we know from the previous means that is about Z score. We have not discussed that part, but try to understand what is Z score. 3.56 is exceptionally large. It appears that in addition to being more than half, means more than half, this is more than half if it is greater than 3.56 or equal to 3.56, and then we can say that more than half, the sample result of 56% is significantly more than 50%. Here sample proportion is whatever proportion we are getting, 0.56, because here we are taking the proportion equation, so that is the statistics we are using, proportions. So sample proportion of peanuts 0.56, or in that case test statistics equal to Z equal to 3.56. so obviously that value lies here. So proportion of adult drivers admitting that they run red lights are in this area, and here we are taking sigma or alpha equal to 0.05, used as criterion for identifying unusually high sample proportion. So these are unusually random samples. Whatever samples comes in that region of the normal distribution or binomial distribution, then we can say that these values are unusually high sample proportion. So our value coming as 3.56 says that happening of that event is highly rare. So that critical region, what it says, the critical region or rejection region is that set of all values of the test statistics that causes us to reject the null hypothesis. So we can reject the null hypothesis. So what is our null hypothesis? Null hypothesis is p equal to 0.5. So we can reject the null hypothesis. We can accept the alternate hypothesis. To accept the alternate hypothesis, what will be? It will mean, for example, see the red shaded region in the previous figure. Here it says that this is the critical region of this diagram. So whenever that value falls in that area, we can say that null hypothesis is not true. So the significance level alpha is the probability that test statistics will fall in critical region when the null hypothesis is actually true. Significance level denoted by alpha is the probability that the test statistics will fall in the critical region when the null hypothesis is actually true. This is same alpha introduced in section 7.2. Common sources for alpha are 0.5, 0.05, 0.01 or 0.10. A critical value is any value that separates the critical region. So there is critical region and significance level. Here this is the critical region and level is 0.05. 0.05. So that is the level and value. Critical value is any value that separates the critical region where we reject the null hypothesis from the values of the test statistics that do not lead to rejection of the null hypothesis. The critical values depend on the nature of the null hypothesis, the sampling distribution that applies, and the significance level alpha. See the previous figure where the critical value of Z equal to 1.645 and corresponds to the significance level of alpha equal to 0.05. So here critical value is 1.645 and the significance level is 0.05. So in this figure, this is critical value 1.645 and the significance level is 0.05. So in that way, it gives us the way to accept or reject the null hypothesis. That here there is two ways to find that critical region and significance levels significance. The tails in the distribution are the extreme regions bounded by critical values. There are two tails, or right tailed or left tailed test. So again here you can see H not equal to alpha is divided equally between the two tails of the critical region. If H not equal to null, H not means that our statement is using not equal symbol, then means less than or greater than. So our statement, whatever claiming we are doing in case of null hypothesis or in case of alternate hypothesis, if it is using not equal symbol, then we can say that whenever this is true, then we can say that our mean is less than or greater than. But when this is going to be true, when null hypothesis is going to be true, then we have to say that that value is directly equal to the alpha. So here, if H naught false, the value of that Z lies here, then we can say that, or we cannot reject H naught, fail to reject H naught, but the value of Z or significance, or the value of significance level is false in the critical region, then we can directly reject the H naught. Means whenever the value of the Z lies here, we can accept that null hypothesis. But if not, we can directly say that is null hypothesis is true, and alternative hypothesis is true, null hypothesis is false, and that is why we can reject the null hypothesis. But if the value falls in this category, we can directly accept or we can directly reject the alternative hypothesis but accept the null hypothesis. But in case of right tail, only this side, here you can see, if the value of Z naught falls in this region, then we can directly say that null hypothesis fails to reject. We cannot reject the null hypothesis. But the Z value is false in this region, critical region, we can directly say that we can directly reject the null hypothesis. That is why this is right tail. Previously this is two tail, and there is also left tail. When we are using this less than symbol, means it points to left part of the tail. So next point is p-value. The p-value or probability value is the probability of getting a value of the test statistics that is at least as extreme as the one representing the sample data, assuming that the null hypothesis is true. The null hypothesis is rejected if the p-value is very, very small, such as 0.05 or less. So if the p-value is 0.05 or less, then we can reject the null hypothesis and we can accept the alternate hypothesis, that is, it is showing in case of left tail or two tail or right tail. If the p-value or probability value we can get close to 0.5 or less than 0.5, then we can reject the null hypothesis. So conclusion in case of hypothesis testing is that we always test the null hypothesis first. The initial conclusion will always be one of the following: reject the null hypothesis, direct conclusion, or fail to reject the null hypothesis. Now what are the criterion to reject or accept or fail to reject? In case of reject null hypothesis, if the test statistics falls within the critical region, then we can directly reject the null hypothesis. If the test statistics does not fall within the critical region, we cannot reject the null hypothesis. Now how we can find or use the p-value in case of decision criterion? So these statements can be extended using the p-value method. Reject null hypothesis H naught if the p-value less than or equal to alpha, where alpha is the significance level. But we will fail to reject null hypothesis if the p-value is greater than alpha, or alpha is here significance level, and the value of significance might be 0.05 0.01, 0.05 and 0.10. That is your choice and most popularly used choice, but that also differs in different research areas. You can go to the literature why and how we can change or what type of significance level can be chosen in case of your study. But in general, most of the studies people choose 0.05 or 0.10 or 0.01 significance level. So another option, instead of using significance level such as 0.05, simply identify the p-value and leave the decision to the reader. That is also one conclusion we can make out from the p-value. There is again one other idea, that is confidence intervals. Because a confidence interval estimates of a population parameter contains the likely values of that parameter, and we can reject a claim that the population parameter has a value that is not included in the confidence interval. So in the distribution, we can, in the distribution of normal distribution, or it might be binomial distribution, or it might be exponential distribution, we can put some confidence interval during which if that value of probability falls, we can say, or we can claim our statement. But if does not fall in the confidence interval, then we will not include that claim, or we cannot claim that statement. So again here, procedure for finding p-values. Start. What type of test? It might be left tail test, it might be right tail test, or it might be two tail test. So it can, in case of left tail test, p-value equal to area to the left of the test statistics. P-values should be equal to the area to the left of the test statistics to reject the null hypothesis. P-value in case of right tail, p-value equal to area to the right of the test statistics. Then you can directly, this is the test statistics value, z value, and p-value should be equal to the area to the right of the test statistics. Area to the right of the test statistics, left of the test statistics. And if we go two tail, is the test statistics to the right or left of the center? We need to find out. If it is left to the center, then p-value should be equal to twice the area of the left of test statistics, because we are using two tail method. So we are comprising, if the value is left oriented, the p-value is left oriented, then we need to take that critical area twice the area of the left of the test statistics. But if the value p-value is towards the right oriented, then we need to take the twice the area of the right of the test statistics, means twice the critical area. So in the next video I'll continue from these slides. Okay, and actually there are more things to go in this hypothesis testings, and that is why I am taking a long video here, and also tomorrow also, or in the next video also, I'll take a long video for better understanding. If you have, and you might have actually some confusion, and also if you ask questions only, I will also learn something. That is the main point. So if you have any confusion or doubt or anything to share, please let me know. We'll try to meet over Google Meet. That's it. Thank you for now.